In this video, I will be discussing about the proof that the area under the normal distribution curve is equal to 1. We know that the probability density function of a normal probability distribution curve is defined by two parameters, mu and sigma, where mu is the mean of the distribution and the sigma is the standard deviation. And this is equal to 1 over the square root of 2 pi times the standard deviation sigma, quantity multiplied to constant e to the power of negative 1/2 of the quantity of x minus mu all over sigma quantity squared. And we know that this x runs from negative infinity to positive infinity. Also, mu can take a value anywhere from negative infinity to positive infinity here, where the sigma is any positive value. And if you sketch the graph of this normal probability density function, the graph is like this, wherein the center is the mean and the spread is defined by its standard deviation. In other words, any distribution is defined by these two parameters, the mean mu and the standard deviation sigma. So for any given mean mu and a standard deviation sigma, you will come up to a distinct normal distribution curve. And our goal is to find the area under this normal distribution curve. And as you can see, the curve is only asymptotic to the horizontal axis x, which means that the curve doesn't touch the x-axis. So our objective is to come up with a proof that the area under the normal distribution curve is equal to 1. And to find the area, we need to integrate this probability density function of f of x, which is defined by the two parameters mu and sigma, integrating it from negative infinity to positive infinity dx. And we will show that the area is always equal to 1. So at this point, we will start writing our proof here. So let's represent our area as A, and this area can be obtained when you integrate this probability density function of the normal distribution curve, which is equal to 1 over the square root of 2 pi times the standard deviation sigma multiplied to the constant of e to the power negative 1/2 of the quantity x minus mu all over sigma quantity squared, integrating it from negative infinity to positive infinity. So to integrate, we would like to factor out this constant because this is just a constant. So factor it outside the integral symbol. So this is the integral from negative infinity to positive infinity of e to the power of negative 1/2 of x minus the mu all over sigma quantity squared dx. And to do this, we need to represent this second power thing to a variable z. So let's use a dummy variable z, which is equal to x minus mu all over sigma, which is this one here. And if you multiply both sides of the equation by sigma, we have z sigma, which is equal to x minus the mu. And if you add both sides of the equation by mu, we have z sigma plus mu is equal to x. So therefore, our value of x is this one here. And we can find the derivative of this x, which is mu plus sigma z with respect to z. And you notice I write this one in a different order here because sigma is a constant number. So the differential of x is equal to 0 because the derivative of mu, which is a constant, is 0. and the derivative of sigma z is sigma dz. So, in other words, dx is equal to sigma dz here. So, our representation of dx is this one. So instead of writing this one, we will substitute it by z because that is our representation of this x minus mu all over sigma. So to write, we have A, the area, is equal to 1 over the square root of 2 pi times the standard deviation sigma multiplied to the integral from negative infinity to positive infinity of e to the power negative 1/2 z squared, because I substituted the value of this fraction by z. And our dx will be substituted by this one, which is sigma dz here. So if you're going to factor out this constant sigma outside the integral symbol, we have sigma all over the square root of 2 pi times the standard deviation sigma multiplied by the integral of e to the power negative 1/2 of z squared dz, integrating it from negative infinity to positive infinity. Our limits of integration do not change because when our x is infinity, whatever is your mu and sigma, which is positive, the z is just an infinity. So our limits do not change even if we change our variable of integration to z. Now, squaring our area, we have 1 over the square root of 2 pi because the sigma cancels each other times the integral of e to the power negative 1/2 of z squared from negative infinity to positive infinity dz times the same quantity because we are squaring here both sides of the equation. So this is multiplied again by itself, 1 over the square root of 2 pi times the integral of e to the power negative 1/2 of z squared from negative infinity to positive infinity dz. Now at this point, this is very tricky because we need to change the variable of integration of the first integral to a new variable x. So we have a squared, which is equal to 1 over the square root of 2 pi times the integral of e to the power negative 1/2 of x squared dx from negative infinity to positive infinity times 1 over the square root of 2 pi multiplied by the integral from negative infinity to positive infinity of e to the power negative 1/2 of y squared dy. So here, we just change the variable from z to x, and from this integral from z to y. So it is just a change of variable. So we will write here by changing z, 1z to x and other z to y. But we can write this product of two integrals by multiplying these constants here as 1 over the square root of 2 pi quantity squared, because we have two of them here, but this two integral can be written as the double integral of e to the power of negative 1/2 x squared times e to the power negative 1/2 y squared dx dy, and the limits of integration are just the same here from negative infinity to positive infinity. And maybe you are asking, why is this manipulation? And the answer is that we know from our integral calculus subject that the double integral of the product of two functions f of x times g of y dx dy integrating, say for example, from C to D, and this one is from A to B, is just equivalent to the integral of f of x dx from A to B times the integral of g of y dy from C to D. And we see that our integral is a product of these two integrals here, but we write this one as this one. So we just apply these equivalent forms that the product of two integrals is just equivalent to the double integrals of the product of two functions, f of x and g of y. So I will write this one here like a squared is equal to 1 over 2 pi, because the square of the square root cancels each other. So we have the double integral of e to the power negative x squared over 2 minus y squared over 2 dA. So instead of writing dx dy here, I will just write dA, where xy is the plane of integration, and this is integrated over the region of the function. So we just apply the law of exponents here, that when multiplied, we just add the exponents. So simplifying the exponent, we have a squared, which is equal to 1 over 2 pi times the double integral over the region of integration of e to the power negative of x squared plus y squared over 2 dA. And at this time, I will use the change of variables to its polar coordinates from x and y to r. So this is e to the power negative r squared over 2 r dr d theta, where theta is from 0 to 2 pi and r is from 0 to infinity here. And maybe you are asking, how did I do that? I just changed the variable to its corresponding polar coordinates, because x is equal to r cosine theta and y is equal to r sine theta. And if you square both sides, this is x squared equals r squared cosine squared theta. And also y squared is equal to r squared sine squared theta. And adding this x squared and y squared, you will obtain just r squared. So instead of writing x squared plus y squared, I will just write r squared here. But to integrate this one, I need to use another dummy variable u, which is equal to the exponent of this constant e. So this is just equal to negative 1/2 of r squared. So this one is negative 1/2 r squared, and our du of that is negative 1/2 of 2r dr. So simplifying this one, we've got the negative du, which is equal to r dr. So rewriting this expression here, we have a squared, which is equal to 1 over 2 pi times the integral from 0 to 2 pi of the integral of e to the power u, because instead of writing this one, we will write its representation, which is u. So that's eu, but this r dr, we will represent that one by negative du. So this is negative du d theta. But our limits of integration is the u of your r at 0 and your u of your r at infinity. And if you integrate this form, this is equal to 1 over 2 pi of the integral from 0 to 2 pi of negative eu evaluated from 0 to infinity, because your u is 0 when your r is 0 here, and your u is infinity when your r here is infinity. So, substituting back the representation, we have 1 over 2 pi of the integral from 0 to 2 pi of negative e to the power of negative 1/2 r squared from 0 to infinity d theta. So I forgot here to write the d theta of this one here. So this is equal to a squared, which is 1 over 2 pi of the integral from 0 to 2 pi, and applying the concept of limit, because this one is infinity, this is the limit of negative e to the power negative 1/2 of t squared. So instead of writing r, I will use a variable t that is moving to infinity, minus the quantity of negative e to the power negative 1/2 of 0 squared d theta. And we know that this is equal to 1 over 2 pi times the integral from 0 to 2 pi of 0, because when t approaches infinity, but this has a sign of negative, this negative e is a denominator. So when t is infinity, at the denominator, the value goes to 0. And this is added to 1 because the negative of the negative is positive, but when the exponent is 0, this constant e becomes 1 there. So our area squared, which is equal to 1 over 2 pi times the integral from 0 to 2 pi of 1 d theta, can be integrated, that is equal to theta itself, evaluated from 0 to 2 pi. So, evaluating this integral, this is equal to 1 over 2 pi times 2 pi minus 0. And multiplying this 2 pi to 1 over 2 pi, the answer is 1. And taking the square root of both sides, the area is equal to 1. And that shows that the area under the normal distribution curve is equal to 1 all the time. And this is a good place to stop.
If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.